we're going to start by looking at an example with equally likely outcomes. So let me read this to you. Find the probability of a heads or a head in one toss of a fair coin. In each trial or toss, there are two possible outcomes where a head would be considered a success or favorable, and a tail would be considered unfavorable or a failure. We'll let the letter P denote the probability of success in one trial. So P equals the probability of S, or capital S, representing success, but we use the little letter P usually to represent the probability of a success in any single trial. Then for this example, P is 1/2, since we are assuming the coin is fair. So in other words, there's a 50-50 chance of it landing on head. It's not a loaded coin that might tend to land on one side more than the other. We'll let the letter Q denote the probability of failure in one trial. Then for this example, since we have equally likely outcomes, or another way of saying it is since the probability of success is 1/2, then the probability of failure would have to also be 1/2, since the total would have to equal 1, since they are complementary. There's only two possible outcomes, and however many outcomes you have, their probabilities have to add up to 1. Okay, so we have equally likely outcomes in each trial. We'll go on to the next slide. Now we'll look at the case of doing two trials in a row where we have the same probabilities as mentioned before. And we're going to do this with many different solutions could work here, but we're going to look at 3 main solutions. And this is with equally likely events. And then we will also look at a similar example with not equally likely events. So first, this one, we're going to start with the sample space. So the sample space is where you can use a tree diagram or any other listing and counting method to figure out how many different total outcomes are possible in the N trials, in this case 2 trials. So using a tree diagram, if we think of the first event, flipping the coin, we could land on a head or a tail, and then after that, depending on how we did on the first flip, head or tail again. So if you follow the paths in the tree diagram, you could get head and then head again, head and then tail, tail then head, tail then tail. So that is 4 simple outcomes in our sample space. Since we're looking at the probability of having at least one head in 2 tosses, these first 3 are all favorable in the sample space. So since they're equally likely events, we can just say that the probability is 3 out of 4. And that works just fine here. Solution 2, the fundamental counting rule. Pretty much the same thing, except for the fact that you wouldn't take the time to make a tree diagram. Instead, you would figure out that since we have 2 flips, and in each flip there are 2 possible outcomes with replacement, in other words, repetition is allowed, they're independent events, then there would be a total of 2 times 2 equals 4 simple outcomes. So we could know that using the fundamental counting rule without doing the tree diagram. So knowing that there are 4 possible outcomes, there's only one of them, and we don't have to see this listed out, remember, with this method. We would know that there's only one possible way that you wouldn't have at least one head, and that's if both of the flips were tails. So being that we know only 1 out of the 4 are not favorable, that leaves 3 out of 4 that are favorable. So you can actually solve this question without doing the whole tree diagram, even though the tree diagram is nice because it can really help you understand the question better. Okay, so those first 2 solutions are pretty much equivalent. And then we have the solution of using probability rules. So in one of the sections in chapter 4, 4.2 I believe, we learned about the addition rule and the multiplication rule. The addition rule is used when you're doing, when you have several simple events that could all be favorable for a certain compound event you've specified. So if we say our compound event is getting at least one head and two flips, then there are three simple events that would all be satisfactory, and it doesn't matter which one, we would be happy with any one of those. So we use the word or there, which means that it's an addition rule problem. So now you can see how I've put the plus signs in and separated out the probability of heads and then heads, plus the probability of heads and then tails, plus the probability of tail and then head. The and then scenario leads us to want to use the multiplication rule for each individual probability, like so. And since we have equally likely successes and failures, you see 1/2 times 1/2 on all of these. And then of course when we add up these 3/4, we'll have 3 out of 4 again. Okay, so that was 3 solutions with equally likely events with the probability of at least one success in 2 trials. Now we're going to look at something a little bit more interesting. This example says that we want the probability of selecting a B, selecting B in one choice, in at least one choice. The probability of selecting B in at least one is really what it should say. At least one. Actually, I guess I need to reword this whole thing. Find the probability of selecting at least one letter B out of the following items. So we have A, B, C, D, E, F, G, H, I, J. That's 10 possible outcomes, and only the letter B would be considered favorable. Okay. Let the letter P denote the probability of success in one trial. So to get a B in any one trial, it would be 1 out of 10 probability, and it follows that the probability of failure, Q, would be 9 out of 10. Okay, so now we see we have an example where our possible outcomes for each trial are not equally likely. Let's explore the different solutions we saw in the earlier example. So for each trial, we have our probability of success and failure up there. Now find the probability of at least one B in 2 trials with repetition allowed. And again, many solutions would work, but let's look at some of them. First of all, the sample space. Similarly to before, we have selecting letter B or not selecting letter B on the first trial. And then from there on the second trial, again, it branches out. And we have 4 simple outcomes in our sample space, where these first 3 have at least one B. So the common error is to immediately assume that the probability is 3 out of 4 again, but this is not the answer. And why not? Let's look at the next solution and see what happens. So we've skipped from the fundamental counting rule, so just to remind us, earlier we did solution number 1 was constructing the sample space with a tree diagram and listing and counting everything. And then solution 2 was equivalent. It wasn't really much different, but just a shorter way of doing the same approach. So I'm skipping right over solution number 2 to solution number 3, where we're going to use the probability rules. Okay, and so you can see before we had equally likely outcomes for each trial, and so everything came out the same way it did with the tree diagram. But in this example, it's going to be a little different. So once again, we see we have 3 possible outcomes that would satisfy our compound event of at least one. But then if you calculate each probability, it's a little different because now you have the probability of a success is 1 out of 10 squared. Then the probability of success and failure, notice now we don't have the 1/2 times 1/2 because they are different. And then the other direction, the other order. And then when you add those together, you get 19 out of 100, or 0.190. And so that is the reason that the tree diagram method doesn't work just on its own, looking at how many outcomes in your sample space are favorable out of the total. You actually have to consider that each individual probability is calculated differently. And then there's a shorter version of approaching these questions. Instead of trying to figure out all the different ways that could be favorable, since we know that there's only one way that we might have no heads in two trials, or in this case, no letter B's in 2 trials, we just subtract 1 minus the probability of none from 1. Or I said that already, 1 minus the probability of none. And that's because the total probabilities all have to add up to 1, so taking off that 1 probability is going to give us our answer. And you can see what happens here. I end up with this probability for this one event where they're both failures. That's the probability of both failures, 9 over 10 times 9 over 10, or 9 over 10 squared, or 0.9 squared. So we get this, which gives us that, where 1 can be represented by any number over itself, common denominator. Then subtract the numerators to get the correct answer. So right here, this is the best solution. It's the most efficient. I was looking for my highlighter here. I'll just do this. It's the best solution because of the ease of it, the efficiency, and it is the key to unlocking in at least one problem for any number of trials, and regardless of whether you have equally likely events or not, this is really effective. And the problem that I was sent to my email from the assignment, I think like 10 different students sent it to me, and for good reason, as you can tell from my explanation here. This is the same problem as with the letter B, pretty much. Find the probability of at least 1 0 in the last 4 digits of a phone number. So then the items available for each digit in the last 4 digits of the phone number is 0 through 9, with repetition allowed. So the number of favorable events for success, a single 0, and then 9 failures, other numbers that are not zeros. So calculating the probability of just a single 0 in the first position would look like this. But then there are more ways to do this, like you could have a 0 in the second position. And how would this be different? Just the order would change, but with multiplication, order changing doesn't matter. So being that the 0 could be here in the first place, or close Outlook so it's not so bothersome, or it could be in the 3rd position or the 4th position. And all of those would have the same probability, so we would be adding all those together, or in other words, 4 times this probability would give us exactly 1 success in 4 trials. Exactly 1. But we're talking about at least 1 0. So once again, we're going to be thinking about, okay, well, what are all the different possible simple events? And let me just show you before I get too far with this. What we could do is we could do a tree diagram. We could say, okay, we could have a success or a failure in the first trial. We could have a success or a failure in the second trial, and so on. And you can see how much time this takes just for 4 trials. And we will see examples with many more than 4 trials. So it's important to get the little tips and tricks down. Although you can use those little tips and tricks in the wrong places if you don't understand them, which is why it's important to go through the long way so that you can understand the full picture. All right, so now you can see I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pathways for selecting 4 digits of a phone number where a success would be a 0 and a failure would be a non-zero digit. And we could have figured that out with the fundamental counting rule also. Picturing these as the 4 digits, the last 4 digits of our phone number. There are 10 ways to choose each one of those. Oops, I meant to say there's not 10 ways to choose. There are 10 ways to choose each one, but since we're boiling it down to either 0 or non-zero, there's really only 2 possible outcomes, success or failure. And so if I started to list and count all the different simple outcomes, I'm going to use Excel to help me organize this, because you could follow the pathways down, go success, 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 success. That's one simple outcome. Success, 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 failure. That's another outcome. Success, success, failure, success, and so on. But there's a more organized way to do it, and that is constructing a probability distribution. So I'm going to show you that. So here we have 4 trials where the probability of success is 1 out of 10 or 0.1, and the probability of failure, which is always 1 minus p, is 9 out of 10 or 0.9. That means that if x is representing the number, oh, I have a different example here. Let me just change it back to number of zeros in last four digits. Okay, so all right, now we could have no zeros in those last 4 digits, or 1 0, or exactly 2 zeros, or exactly 3 zeros, or exactly 4 zeros. And the number of ways that we can do this, well, you could have success, or excuse me, if you have no successes, no zeros, then that could be failure, 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 failure. And that's the only way to get it. With exactly 1 success, that could be success, failure, 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 or the success in the second position, or the third, or the fourth. And then for 2 successes, well, that could be, actually before I do the 2, because that one's actually the hardest one to think about, let's think about the easier one. So we did 0 successes where you had all failures, or you could think about all successes, and there's only one way to get that. And then we thought about 1 success, where the success could be in any of the 4 positions. And if we think about 3 successes, then you can think about where the failure is, the single failure. So the failure could be first, could be second, could be third, or last. So there's 4 of those. And then for 2, just a little bit more complex, not so bad, but you can imagine when you start getting up into higher and higher number of trials, this can be a very inefficient way of doing things. But this is for understanding, and then we'll see how the tricks work. So we're going to do the successes maybe in the first 2 trials, or maybe in the last 2 trials. How about the outer trials or the inner trials? And we could also do alternating like that, where you start with a success, or alternating where you start with a failure. So there's 6 ways. And the probability for all failures, oh, and let me just say, if that seemed hard for you to try to, you can imagine how you could accidentally miss one of these when you're just thinking about it in this way. That's why the tree diagram can be such a help, because it gives you a process so that you don't miss anything. But this is a nice organized way to get things together. And so now we can look at the probability of failure in 4 trials. Well, that would be 0.1 times 0.1 times 0.1 times 0.1, right? Failure, then failure. Oh, wait a minute. Sorry. I meant to say 0.9, because these are all failures, and the probability of not getting a 0 is much higher. 0.9 times 0.9. There you go. So that gives you the probability of having all failures right there. And the probability of success is just the opposite. It's 0.1 times 0.1 times 0.1 times 0.1. And many of you are thinking, well, why don't you just do the power of 4? Yeah, that's smart, right? Here, why don't we just do the power of 4? Okay, and then for this one, we could have 0.1 for the, let's look at this first trial here, SFFF. So 0.1 is the probability of success, then 0.9 times 0.9 times 0.9. I must have put my cursor in the wrong place. Try that again. 0.1 times 0.9 times 0.9 times 0.9. However, I only did it for that first event. Remember, there's 4 of them, and either one of any of them would work. It would be fine if it was the first position or the second position or the third or the fourth. So we'll need to do the addition rule here. So for the second trial, it's 0.9 for the first failure times 0.1 times, that was the success, and then 2 failures, 0.9 times 0.9. And so far we've just gone with 2 of them, and then we can do it again. For the third one, fail, fail, succeed, fail. So that's fail, fail, succeed, fail. And now the last one, plus fail, 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 succeed. Fail, 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 succeed. All right, so that's the probability of having exactly 1 success in 4 trials. And as you can imagine, we could go ahead and keep doing this, but there is actually a better way, just focusing on this one. Since there are 4 trials like this, and the only thing that is changing is the order in which we're doing this multiplication of 3 0.9s and a single 0.1. And you know, multiplication is commutative. You can do 2 times 3 to get 6 or 3 times 2 to get 6. So actually, each of these have the same probability of occurring, and repeated addition is multiplication. So instead of doing this plus this plus this plus this, I can just do 4 times any one of them. So that's what I'm going to show you. You see the answer now, 0.2916. And if I just change this to be, I'm going to take away all the other events, and instead I'm just going to say 4 times all that. And there you see the same answer. And then you can do that for any of these, right? So since there were 6 of these, it'll be equal to 6 times 2 successes and 2 failures. Then this will be 4 times 3 successes times 1 failure. And then you might have noticed also, like for this one, that could have been 0.1 squared, 0.1 to the power of 2 successes. And this could have been 0.9 squared, 0.9, 2 failures. And notice that those exponents here and here will always add up to 4 or to n. Here we could have done 0.1 to the power of 3. And just to keep with the exponential thing, we could do 0.9 to the power of 1 failure. All right, and then there's something else cool too that you can do with Excel. I'm running out of time. I'm going to have to stop soon, but maybe if there's more questions about this, I can do more later. Okay, so I was going to just show, let me put in another, temporarily put in another column. We listed and counted these to figure out that there was 1 way to get exactly 0 successes, 4 ways to get exactly 1 success, 6 ways to get exactly 2, and so on. But we learned about a counting rule in 4.6, the combinations rule. And that will work here, except instead of R, we'll say X, like the number of successes. So N is the number of trials and X is the number of successes. So if I just do the combine function and choose N is 4, and I'm talking about 0 successes here, there's only one way to make that happen. And then again, 4 trials with 1 success, there's 4 ways for that to happen. And you can make it programmed with an absolute reference here. Instead of typing in 4, you can refer to a cell containing your N, but make sure to F4 that so it stays the same for each row when you copy it down. And then instead of typing in 0, you can actually click on the cell containing your X value. And that one you don't want to be absolute, you do want it to stay relative, so it will change as you copy the formula down. And so then this formula could be made, this process can be made even easier so that you don't have to list and count things, because then you can just do the NCX times 0.9 to the power of 4 successes times let me say it in a different order, 0.1 to the power of no successes. And remember, anything to the power of 0 is 1, and 0.9 to the power of all 4 successes. Notice that's the same answer as before. Here, instead of having 4, we could have used the combinations. And so it just goes on from here, and you can even program it more and more specifically. Like instead of typing in the 0 on the power of the probability of success here, you could have just clicked here. It stays the same. Also, instead of this, you could have done n minus. So since the 2 exponents have to add up to n, you can do n F4 minus however many successes you have. And that would give you 4 minus 0 would give you 4, right? So, and that will work, and watch how these are all going to stay the same when I copy that down. Cool, right? Okay, just as the cherry on top, this is actually a binomial distribution, which I don't have time to get into detail about, but the requirements are 4. I'm just going to say them instead of writing them out. Number 1, you have to have only 2 outcomes per trial, which should make sense to us because it's binomial. So that can help you remember 2 possible outcomes for each trial. That's one requirement. That's usually the giveaway. But then you have to also make sure that you have a fixed number of trials. So like in this case, we have 4 trials. You also need independent events. So like in this case, repetition was allowed for all the digits of the phone number. And the probability of success has to be the same in each trial. So in this case, we had a probability of getting a 0 in each trial was always 1 out of 10. Same in each trial. So those requirements are satisfied for this example. And there's a formula. The binomial formula looks like this. And notice that it has the combinations, then the probability of success to the number of successes, probability of failure to the leftover, the rest of the trials, which is exactly what I derived with you as we went through this process. So I'm going to show you how there is a function that you can use to verify this binom.distribution. And notice that it wants the number of successes first, which would be here, comma, the number of trials, which would be, you could just type 4, or if you want to use an absolute reference to this, F4 puts those $ in so that the references don't move. You can also type those $ in yourself. And then the probability of success in each trial, we also want that to stay static or absolute. And do we want cumulative is the next thing it asks us. And you can type in 0 for no or 1 for yes. Or you can double click true or double click false. We're not doing cumulative right now. We're doing the probability of an exact number of successes right now. So I'm going to choose false. Or again, like I just said a moment ago, you can even just type in 0 which also reads as false for that argument. Copying it down, you can see all works out. This one down here, let me explain what that's about. When you construct a probability distribution, which when it's more simplified, it looks like this: 0, 1, 2, 3, 4, and then the probability of success. I'm just going to refer to these cells that we already calculated. When you add up all your probabilities, if you've done it correctly, they'll add up to 1. So there's two things to check for probability distribution. Okay, probability distribution is introduced in 5.1, and I did a whole nother video just on this also, which I think I need to stop right here because I'm about to go to class. And I did all of this, and I continued on, and I did a couple more examples in another video. So check that one out. I hope this helped. Let me know if you liked it, or if you have any comments for suggestions. Constructive criticism is always appreciated, and I will see you in class.